Okay, welcome back. This is part 2 for test 4 review, and we're into now, so we just did the substitution section. Now we want to look at 5.7, which is basically, I think it's just more substitution, but with a natural log involved. Okay, so 5.7, we're thinking of questions like 5 to 41 odd, then 51 to 57 odd. Okay. Right, so let's dive right in. Let's look at number 7. So we have the integral of 1 all over 2x plus 5 dx. And right, so the kind of deal here, you want to identify kind of a form, right? If it loosely has this form of the integral of 1 over something, hopefully you can pull off a u sub to put it into that form at least. And then the integral of that is the natural log of the absolute value of x plus c. Okay, so that's the thing you need to kind of have encoded in your brain. And okay, so we're going to let u equal this, because then we're going to have 1 over u, and then we'll have ln of u, right? So let your u sub be 2x plus 5, and then your du is 2 dx. And then I like to solve for dx is just du over 2. Okay. So this will be the integral of 1 all over u times dx, which is du over 2. You can factor out the 1/2. So you get 1/2 integral of du over u. And that's just the natural log, right? So you can always rewrite these things, and this 1 over x dx is the same as the integral of dx over x, which is the same as the integral of x to the negative 1 dx. But hopefully you can appreciate this thing right here is just the natural log of the absolute value of u, right? So this will be 1/2 natural log absolute value u plus c. And then that's equal to 1/2 natural log absolute value back sub 2x plus 5 plus c. Okay, so very fairly simple. Let's move on. Let's see. Sure. Let's try 17. So we have the integral of x squared minus 3x plus 2 all over x plus 1 dx. Okay. You could try to factor this thing and hope for a cancellation. Is that really going to cancel? This one ain't going to cancel. So if it's not going to cancel, your only other option is really to do long division. Okay, so x plus 1, and you probably have had to do long division for finding asymptotes, slant asymptotes. Okay, that's probably the last time you did it. But anyways, this is how it works. So you put the numerator inside the division symbol, the denominator on the outside, and you ask yourself, what times x is x squared? That would be x. So x times x is x squared. X times 1, you just distribute the x to this binomial, so you get plus x. And then you subtract. Okay. So x squared minus x squared is 0. And negative 3x, and you have to distribute this negative to both, right? So it'd be negative 3x minus x is negative 4x. Bring down the next term. Then you ask yourself, what times x is negative 4x? Well, negative 4. So you'd have negative 4x, and you distribute this negative 4 to both terms, so minus 4, and we subtract. Okay. So negative 4x plus 4x is 0. 2, negative plus 4 is 6. And as soon as the degree of this is less than the degree of this, you're done. Right? And you could write up your answer, so, quote unquote answer. Okay? So the way it goes, it's x minus 4 and then plus the fraction built by putting that all over that. Okay? So what? It's x minus 4 plus 6 all over x plus 1. And then dx. Okay, so the first two parts of the integral we can do. So integral of x is x squared over 2. And then the integral of negative 4 is just negative 4x. And then plus we do the integral of this, right? It's just going to be 6 ln absolute value x plus 1, okay, plus c. So why is that? Well, let's take a closer look at the integral of 6 over x plus 1. Right. Let's take a closer look. The integral of 6 over x plus 1 dx. So you can automatically factor out the 6, and you just get 1 all over x plus 1 dx. If there's no constant in front of this x, so if it's not, you can't even have a negative in front, then when you find your u sub and get your differential, it's not going to have a constant or anything. It's just going to be du is equal to dx. Okay, so ultimately it's no different than just saying, okay, the ln of u is equal, in this case, equal to the ln of x plus 1. Okay, so if you're not convinced, let me do the u sub. U is x plus 1. And you see du is just going to be dx. Okay? There's no constant to worry about. So when you go to your integral here, you have 6 integral of 1 over u times du, and that's just the ln of absolute value of u plus c, and then you back substitute and you get 6 ln absolute value of x plus 1. So the point of my story is just treat this whole thing as a variable, and you're finding it, so if you have the integral of 1 all over, I don't know, x minus 8 dx, that's just going to equal the ln of the absolute value of x minus 8. Okay. You can't always pull that though, right? Because we saw in our problem 7, 1 all over 2x plus 5 dx, its integral is not the ln of the absolute value of 2x plus 5. No, when you find that differential part, you do all the u sub material, you have a constant of 1/2 to end up having to pull out. Okay, so, there's little tricks you can do, but you just have to be kind of careful because you'll end up maybe accidentally being off by a constant multiple. Okay, so getting back to here, the integral of 6 over x plus 1 is just 6 ln of x plus 1 plus c. And then that would be our answer for 17. Oh, what else? I guess 24, let's try 25, looks kind of annoying. Right? So 25, the integral of 1 all over the square root of x times 1 minus 3 square root of x dx. Okay, so it's my usual program, if I was going to make a computer program to do integrals, and the first artificial intelligence programs were computer programs. I think it was like Slagle was the guy's name from MIT. His PhD thesis was on taking the final exam from a Calc 1 class and writing a computer program to answer all the questions. And he was able to get like a 96% on the final exam with his computer program. And it was all doing integrals. It was just integral, integral, integral. So if you're interested in that, you could look it up. I've read most of it, and I used to assign it for extra credit in Calc 2. So his thesis, it was the Saint program, I think, S-A-I-N-T. And I forget the dude's name, but I think it's Slagle, or S-L-E-G-E-L, or some variation, S-L-A-G-E-L. He's at MIT, or was at MIT. I don't know if he's there anymore. He's probably deceased by now, but yeah, that was one of the first artificial intelligence programs written, where these programs where you try to get the computer to do something that other people think the computer can't do. The computer isn't a thinking being because it can't do blank, and you write a computer program to get it to do whatever that blank is. That's kind of an archaic way of thinking of artificial intelligence programming. Okay, so anyways, there's that junk. U sub, right? So I want to do a U sub for this. My program says just look for the parentheses and do whatever in there. So U is 1 minus 3 square root x. Okay, and then my du is negative 3 times 1/2 x to the negative 1/2 dx. Okay? And then I want to solve for dx. So dx equals negative 2 all over 3, so it's the reciprocal of this material here, times x to the positive 1/2 now, and then du. Okay, and so I'm going to do my replacements and hope everything cancels. So I get 1 all over the square root of x times u times du, which is now negative 2/3 x to the 1/2 du. Okay. And certainly the x to the 1/2 will cancel. You could factor out a negative 2/3. And you get the integral of 1 over u du, which is sort of our integral du jour. And that will be negative 2/3 ln absolute value of u plus c. And then finally back sub negative 2/3 ln absolute value 1 minus 3 square root x absolute value plus c. Okay? All right, yay. Let's look at some other ones. Well, certainly now we can kind of integrate any trig function that we want to. I guess we look at 39. Is that in our list? Yeah. So let's say 39. Got the integral of secant x tan x all over secant x minus 1 dx. Okay, right. So how do I get this one to work out? That's a good question. I kind of want to multiply top and bottom by secant x plus 1 and kind of see where that goes. But I'm afraid I might be going down a rabbit hole. What else can I do? I think that's got to be it. So I'm going to try that. If it doesn't work, I'll just back up and do something else. So you're going to end up with secant x tan x times secant x plus 1 all over secant x. If you multiply secant x minus 1 times secant x plus 1, you'll get secant squared minus 1 dx. And then we could go to our Pythagorean identities, right? So we would have 1 plus tan squared x is equal to secant squared x, and then tan squared x would be equal to secant squared x minus 1. Okay, so using that identity, I'm going to replace the denominator, and that should hopefully work out nice for us, or relatively nice, I guess. So we get secant x tan x times secant x plus 1 all over tan squared x. Ugh, not very nice still. At least we get a little cancellation with the tan material. So we get a secant x times secant x plus 1 all over 1 factor of tan x dx. And then what? Yeah. Let u equal, well, I don't want to do that, right? But let's clean this up a bit and rewrite it. So I have, if I distribute, it would be secant squared x plus secant x all over tan x, right? And then I want to butterfly it, right? So I'm going to have secant squared x all over tan x, and then plus secant x over tan x dx. Okay, and then I'm going to, on this guy, I can do a u sub now for u equals tan x. On this guy, I'm hoping I can do some clever kind of cancellation. So note that secant x over tan x, if I write it, if I go back to sines and cosines, this is the same as 1 all over cosine x times 1 over tan, which is the same as cotan, which is cosine x over sine x. In other words, this thing is really equal to 1 over sine x, which is really equal to cosecant x. Okay, and then I have formulas for that. I wouldn't expect it to have that memorized, though. So let me just recap which trig integrals you should have memorized here in a sec. But let me get this out of the way. All right, so right now I'm looking at an integral for secant squared x over tan x, and then plus this other integral for cosecant x. So this would be dx and then cosecant x dx. So the first integral, I got to do a u sub for tan x, and then du will be secant squared x dx, which is sitting right here, right? So I can replace the numerator of that expression with just the du, and it will be all over u. Okay? And then plus this integral, which is an awful lot like the integral of secant. So I think it's just probably negative ln of the absolute value of something like cosecant plus cotan, which I don't expect you to have memorized, right? Let me just make sure that's right before I commit. So I'm going to go to my book, and hopefully these integrals are in my book somewhere. If not, I'm going to be ticked. Pre-calc review. Here's my integral table. So cosecant ln. Oops. No, I am right. That's negative ln cosecant plus cotan. Yeah. There's two versions, but that's one of them. Okay, so then this other integral, the integral of du over u, is the ln of u, ln of absolute value of u. Okay, so minus ln absolute value cosecant x plus cotan x. C. Then, well, I mean, you're going to have your book anyways, so you'll be able to look up integrals if you need to. Okay, so I'm not going to. Maybe I should tell you for people who are moving on. Ln of the absolute value of tan x when I back substitute minus ln absolute value of cosecant x plus cotan x plus c. That's your answer. But anyways, the integrals that you should have memorized if you're going to take like Calc 2. So you have the standard integrals that you should know. So sine x dx, integral of that is negative cosine x plus c. The integral of cosine x dx is sine x plus c. The integral of and then you kind of think in terms of antiderivatives, right? So you're not necessarily going to put the integral of tan next. You put the integral of secant squared x dx, and then that's tan x plus c. And then you have the integral of cosecant x cotan x dx, and that's negative cosecant x plus c. Integral of secant x tan x dx is equal to secant x plus c. Integral of cosecant squared x dx is negative cotan x plus c. Okay, so these are standard. It's just because you have the derivatives memorized. You know the derivative of sine x is cosine x, so the integral of cosine x must be sine x. Okay, you should have those derivatives and integrals memorized. Then, because of this section with u subs and natural logs, we can also kind of have some other integrals maybe memorized, right? So the integral of tan x is going to be the ln of the absolute value of secant x plus c, right? And that would be the only other one that I would expect people to kind of know. Some teachers may think that you should know secant x tan x dx, which is ln of the absolute value of secant x plus tan x. But I generally wouldn't expect people to have that memorized if you have a life of some sort. One thing that students always argue with me, well, no, it's supposed to be negative ln of cosine, right? Well, yeah, kind of. So remember when we did our integral of tan x dx, what was that? Well, that's the same as writing out the integral of sine x over cosine x dx, and then you do a u sub on cosine. Okay, And so you have the integral of sine x over cosine x times du over sine x. The sine x's cancel. We replaced cosine with a u, right? So you'd end up the integral of du over u, and then that's the ln of the absolute value of u plus c, and then that's equal to the ln of the absolute value of cosine x plus c, where this should be negative. I totally apologize. So this would be down here a negative, so we could factor out a negative, that would be negative, that would be negative there. Okay, but hey, why did I write ln of absolute value of secant? Well, I did that because this negative, you can bring it inside. You could use the power rule for natural logs to rewrite ln of the absolute value of cosine of x to the negative 1 plus c. And then we all know cosine to the negative 1 is the same as 1 over cosine plus c. And then 1 over cosine is secant. Okay, so generally that's the way I write it, because that's the way my book taught me how to do it. Okay, but your book is teaching you a different way, which is fine too. It's the same answer. So long story short, what I would expect from you memorized, if I was giving you that kind of test, would be those basic integrals there with regards to trig, right? On top of that, I would expect you to have all of your standard Pythagorean identities kind of memorized. I hit the stupid webcam. Now everything's screwed up. Hold on. Make sure it's on. Okay, it's okay. All right, so, you know, those guys you should know like the back of your hand. Okay. Let's move. Let's see if I can move on. 57, 51 to 57. I mean, I don't think we looked at any of those. I think that's probably just evaluating, right? Yeah, those are just evaluate the integral. You try one of them. Okay, let's try 53. Or maybe we could try a more challenging one. Let's try 57. No, let's try 53. There's a natural log in there. I like that one. So the integral of 1 to e of 1 plus ln of x squared all over x dx. Okay. And my program in my brain is usually like, just let the u sub be the stuff inside the parentheses, so 1 plus ln of x du, derivative of 1 is 0, derivative of ln of x is 1 over x dx. I like to solve for dx. Multiply both sides by x, you get x du. Okay. If you want to, you can rewrite your limits. I'm going to wait and back substitute. Okay, so I got my new integral. 1 plus u is now u. 1 plus ln x is now u squared all over x times dx, which is now x du. So the x's divide out, and you're left with the integral of u squared du, which is u cubed over 3 du. And then I'm back subbing. So that's equal to 1 plus ln x cubed all over 3 from 1 to e. Whoops, I abused my notation. So once you integrate, you get rid of the du, you get rid of the integral symbol, and all you should have, if it's a definite integral, is that bar there. I didn't put the limits in here because I'm still in terms of u, and that wouldn't be true. I would not be evaluating from 1 to e here. I would have to rewrite it with using this formula. Once I get back in the x, now I can rewrite my limits in there. Okay, so now I evaluate. I have 1 plus ln of e. ln of e is 1. Okay, so 1 plus 1 cubed all over 3 minus 1 plus ln of 1. ln of 1 is just 0. And then 1 cubed is 1 all over 3. Okay, so this will be 2 cubed is 8 thirds minus 1 third. And that'll be 7 thirds. Okay, so a bunch of those on the test. The 5.8 is the next section. Okay, and in that case, we want questions like 3 to 45 odd. And those were inverse trig. So the two main formulas, if you are memorizing things for my test, and on my test I'll probably focus in on these formulas, the two main formulas should be the following: the integral of du all over 1 plus u squared, or rather a squared plus u squared is 1 all over a tan inverse of u all over a plus c. And then that other guy we need is du all over the square root of a squared minus u squared is 1 all over a, just sine inverse of u all over a plus c. Okay, so if this was a real non-pandemic year, I would force you to memorize these. Okay? You should memorize them. Note cards. Okay, just basic as knowing your multiplication tables. So I won't call upon you to do the other ones where you're having to find the, do they also give you the derivatives in this section? No, it's just the integrals. Okay, so we're looking at questions, 3 to 45? So let's try number 5, I guess. So we have the integral of 1 all over x times the square root of 4x squared minus 1 dx. Okay, so I'll let, this time I'm not going to do my program. Okay, well, maybe I should, right? No, I'm not going to do my program. See if you, no, I should do my program. Let u equal this, and it's not even a inverse trig integral. Right, so u is, let me make sure, 4x squared minus 1 du is 8x dx. No, it is. It is some sort of, it must be like one of those secant inverses or something. I'm not worried about secant inverses. Let's just for the sake of completion, let's do this one. It is the secant inverse guy, right? So in this case, the secant inverse formula is the integral du all over u times the square root of u squared minus a squared. So essentially we want to identify u, identify a, and once we do, we can just dump it into this formula, which is 1 all over a secant inverse of absolute value of u all over a plus c. Okay. So in this case, what is u? Well, u is going to be the square root of this thing right here. Okay, and then a is going to be 1. All right, so we'll let u be 2x, and then du should be 2 dx, and then dx is du over 2. Okay. So I have to go back through here and do my replacements. Okay, so that my integral will become the integral of 1 all over x. And if I use this equation to rewrite x, it'll be x equals u over 2. Right, so I'd have 1 all over u all over 2 times the square root of u squared minus 1 times du, times dx, which is now du over 2. Okay. There's somebody at my door. Frick. Seriously? Okay, so anyways, this is 1 over 2 down there. You can sort of multiply everything by 2 in the denominator if you want to think of it that way. 2 times u over 2 will just give you u. So this will be the integral of du all over u times the square root of u squared minus 1. Okay, and that is literally just a secant inverse formula where a is equal to 1. So we'll have this equal to secant inverse of absolute value of u all over a, which is 1 again, plus c, and then back sub, so you get secant inverse of absolute value of 2x plus c. Okay. All right, I didn't want to do that one. That's what I get for not preparing my lessons. But there it is. Okay, so let's look at another guy. Crap, now I just went over the... Okay, so another guy. try. Let's try number 17. I'm hopeful for number 17 to be an inverse sine. So this is 1 all over the square root of x times the square root of 1 minus x dx. And this guy looks an awful lot like the secant inverse, but I don't think it is. So how am I going to, figure this one out? Well, I'm going to rewrite this thing as the square of something. Okay, so what is it the square of? Well, it's the square of the square root of x. So this will be the square root of x squared. And then I can do my u sub for that thing, and it'll get into, hopefully, the form 1 over square root of 1 minus u squared, right? So if you let u equal the square root of x, which is x to the 1/2, the differential du is 1/2 x to the negative 1/2 dx, and then multiply both sides by 2x to the 1/2, and you get dx is equal to 2x to the 1/2 du. Okay, so this integral should be 1 all over, square root of x, or x to the 1/2, if you rather, times the square root of 1 minus u squared now, times dx, which is now 2x to the 1/2 du. And sure enough, the x to the 1/2s cancel, leaving you with an inverse sine integral. So 1 all over the square root of 1 minus u squared du. And of course, that's just 2 sine inverse of u plus c. And then back sub, so 2 sine inverse of x to the 1/2 plus c. Those are all kind of out there. Let's do one that's a little easier before I kind of look down further. Let's try number 9. And we have the integral of t all over the square root of 1 minus t to the 4th dt. Okay, so you're trying to get it into the form of the arc sine or the arc tan, and so you want like 1 minus u squared. So let u equal t squared. And then when you do your replacement, this thing will be 1 minus u squared. Right? Okay, so du is 2t dt, and then dt will be du all over 2t. So subbing, I get t all over the square root of 1 minus u squared times dt, which is du over 2t. T's cancel, you can factor out 1/2, and you're left with the integral, which is an inverse sine integral. We need an inverse tan integral somewhere. So you get 1/2 sine inverse of u, which is t squared. Let's just cut to the chase. Let's see. Oh, hopefully I can find a freaking tan. So I'll go back to number 8, I suppose. Let's try 8. So I got the integral of 7 all over 4 plus 3 minus x squared dx. So I want something like a squared plus u squared. So let the u equal 3 minus x. And then du will be negative, the derivative of 3 is 0, the derivative of negative x is negative 1, and then dx. So dx is negative du. Okay. So I'm ending up with my integral. I can factor out the 7. So I have 7 integral of 1 all over something squared, which is 4. So 2 squared. So a is 2. Plus u squared, and then dx is now negative du. If you factor out the negative, you get negative 7, and then we have an integral of 1 all over a squared plus u squared du, where our a value is 2. So that would be negative 7 times 1 over a, so 1 over 2, times tan inverse of u all over a plus c. And then finally back substitute. So I'm getting negative 7/2 tan inverse of u, which is 3 minus x all over 2, and then plus my integration constant. Okay. Okie dokie. So that would be the answer on that guy. They get a little more annoying when you have to actually evaluate them, do definite integrals. These are, I just did a bunch of indefinite integrals, right? Let me scroll down a bit. Let's try number 29. And then we'll move on. So I got the integral from 0 to the ln of 5 of e to the x all over 1 plus e to the 2x dx. Okay, so this looks like an inverse tan. I'm going to replace e to the 2x, or rather just let u equal e to the x, right? Because then e to the 2x is the same thing as, over here, what is e to the 2x, right? E to the 2x is the same thing as e to the x squared, right? So if you let u equal e to the x, then our differential du is e to the x dx, and then dx is du over e to the x. You'll see it's an inverse tan integral, right? So you have e to the x all over 1 plus u e to the x squared times dx, which is now du over e to the x. Right? And then the e to the x's cancel, and you just have a nice inverse tan formula. So 1 over a is 1, so I just get 1 times tan inverse of u over a, so just u plus c, and then back substitute. Oh, we're evaluating, so it's not a plus c. Whenever you evaluate, do not write plus c like I just did. Okay, that's a big no-no. So you get tan inverse of u, which is e to the x. And now go ahead and evaluate. So I back subbed. I can put in my limits. So this will be tan inverse of e to the ln 5. E to the ln 5 is just going to be 5, right? Because e to the ln, those will kind of cancel and you just get 5. Minus tan inverse of e to the 0, which is 1. So this will be tan inverse of 5. So again, e and the ln's cancel. Minus tan inverse of 1 is just pi over 4. Okay? So tan inverse of 5 minus pi over 4 for your final answer. Okay. One last section, 5.9. So 5.9, we're looking at problems like 25 to 33 odd, and then 45 to 59 odd. In particular, we're just worried about derivatives of the hyperbolics and integrals of the hyperbolics. We're not going to worry about the inverse hyperbolics. It turns out we're not going to use those very much in Calc 1, in Calc 2 or Calc 3. I don't know if you use them in your engineering program. You probably do if you do particular kinds of engineering, for modeling or something like that, but I don't know. Okay, so I apologize if you use this extensively, but at least I showed it to you, right? So anyways, 5.9, hyperbolics. So if you know the derivatives of the trig function, you should know the derivatives and therefore also the integrals of the hyperbolics. So the derivative of sinh is just cosh. The derivative of cosh is just sinh. The derivative of tanh is just sech squared. So the main difference is the negatives, right? And all these derivatives on this side are all negative. So the derivative of sech is negative sech coth. The derivative of cosech is negative cosech. Sorry, this should just be tanh up here. Secant tan, so sech tanh. This will be cosech, cotanh, or coth. Sorry, my other computer is trying to get me next tomorrow. Okay, thank you. The final one, the derivative with respect to x of cosech, or sorry, coth, is negative cosech squared. Okay. So it wouldn't be a bridge too far to ask you to have these memorized. And then likewise the integrals, so just a random integral, the integral of cosech x cos x, of course, is just going to be negative cosec x plus c, right? Okay, so let's see what the book has with regards to those types of problems. This is now 5.9, the last section that will be on the test. And let's take a look. So just looking at derivatives and integrals of these hyperbolics. First, let's maybe look at some integrals. So 23 to 33. So chain rule stuff. Let's look at 27, I guess. Find the derivative of y equals hyperbolic secant of 5x squared. So chain rule, and you could do it with kind of the pieces. So the inner piece is 5x squared, and the outer piece y equals hyperbolic secant of that u part. And then your derivative is just take the derivative of this times the derivative of that. So it'll be negative hyperbolic secant of u tanh of u times the derivative of 5x squared, which is 10x. And then you back sub, right? So this would be negative, let me put the 10x in front. So 10x, negative 10x, hyperbolic secant of 5x squared, hyperbolic tangent of 5x squared. Okay. Assuming I got the formula right. Seems like it's right, but let me make sure. I hate to think that I'm telling you the wrong thing. So no inverse hyperbolics, none of that. Yeah, I'm right. I'm good. All right, let's look at another derivative. As soon as I get my computer back on board. Okay, another derivative. Let's try 34. So what do we have? G of x equals hyperbolic secant squared of 3x. Again, if you need to put it in the pieces, so you can rewrite this first off, hyperbolic secant of 3x, and then all of that is squared. Okay, so the innermost part is the 3x, and then if you step up one level, you could say v is equal to hyperbolic secant of u, and then if you step out one more level, y is equal to v squared. Right? And if you back subbed all this, you would get g of x, right? So if you if you take y, and that's going to be equal to v squared. V is secant of u, right? So v squared is that of u, and u is 3x. So from this information, you can reconstruct the original formula. Okay. So anyways, take the derivatives, just the derivative of this times derivative of that times derivative of that. So y prime is 2v times negative hyperbolic secant u hyperbolic tan u times the derivative of 3x, which is 3. And clean that up. So that'll be 6 times v, which is hyperbolic secant of u times negative secant of u tanh of u, and then you can pull out the negative, so this would be negative 6 hyperbolic secant squared of u, and u is 3x, so let's just cut to the chase, times hyperbolic tangent of u, where u is 3x. Okay, that's a hard one. Okay, let's move on to the integrals. So now looking at problems like 45 to 59. So let's try 47. I'm running out of paper, so I had to settle for this paper I've already used for other stuff. That's why you see all the funny numbers on it. Anyways, 47, the integral of sinh of 1 minus 2x dx. Looks like we'll need a u sub, so let u equal 1 minus 2x. So du is negative 2 dx. Dx then is negative du over 2. Okay. So the integral of hyperbolic sine of now u times dx, which is now negative du over 2. You can factor out a negative 1/2, so negative 1/2 integral hyperbolic sine of u du. Integral of hyperbolic sine is just hyperbolic cosine, so negative 1/2 cosh of u plus c. Back substitute negative 1/2 cosh of 1 minus 2x plus c. Let's just do one more, and then I'll call it quits. Maybe try a harder one. I don't know if any of them are all that hard. Let's try 53. Okay, so we have the integral of x times cosecant, hyperbolic cosecant squared of x squared over 2 dx. Okay. Let u equal the stuff here in the parentheses, so x squared over 2. Take its derivative. The differential du is 2x over 2, which will just be x dx. So dx is equal to du over x. Okay, do your subs. So x times hyperbolic cosecant squared of u times dx, which is now du over x. The x's cancel. Integral of hyperbolic cosecant squared of u du. Integral of hyperbolic cosecant squared is just hyperbolic cotan, negative hyperbolic cotan of u plus c. Back substitute, so get negative hyperbolic cotan of x squared over 2 plus c. And that's about it for me. Yeah, okay, that's good. Okay, so I'll be posting your test. It'll be another one of those time tests. I'll be posting it for the Wednesday class on Wednesday, and then for the Thursday class on Thursday. You'll have probably about 3 hours to complete it, and then back upload it. So the way I'm going to want you to submit your test this time is in a PDF form. It is going to kill my computer if I keep allowing you to send me tons of pictures, and then having to personally turn everything into PDFs is too much. It's a bridge too far. So I'll give you links for converting your files into PDFs. I'll put that up as soon as possible so you can practice converting a file into a PDF from a picture. And okay, so yeah, we'll see you next time then.